Hello, everyone. Title of the presentation is Using Multiple Authoritative Servers Does Not Work Like You Thought. Okay, so basically, here's the problem statement here. You've got a single edge provider for your authoritative DNS. Every vendor can have a bad day. So this image here is from the Dyn outage in 2016, a famous outage in the DNS world, which took out a lot of the internet. It was a problem. And I don't mean to pick on any one vendor or other. Basically, any provider can have a bad day. And if you've followed along DNS for any time, you know this is true. So stepping back from that, looking at principles of engineering, you want to remove any single point of failure in your system, right? So redundancy means that any one point of failure isn't going to take your whole system down, right? You have to do it a bit carefully because what you need to make sure they don't actually make your system less reliable. This is a commonly used approach in all kinds of areas. We use it in RAID for our disks, we use it in clustering for servers, and of course the DNS itself is also highly redundant in lots of different ways. Unfortunately, redundancy also increases complexity, which can add new failure modes. So things like network partitioning and things like that are things you have to worry about. So it's not just magical reliability dust you can sprinkle on a system. So how does this apply to DNS authoritative servers? Basically, the DNS, as I mentioned before, has a lot of built-in redundancy. Every zone should have multiple name servers. Each name server should have one or more addresses. So in the end, this means that you have a set of addresses that resolvers can choose from to try to get information about a zone. And in principle, if one of these addresses isn't working, the resolver will pick another one. So usually resolvers are trying to get the fastest results they can, so they tend to maintain a little bit of state about these set of IP addresses and have heuristics about picking the best one for any given name. But again, in general, this means that if one of these doesn't work, you try one that does work. And an authoritative server that isn't up at all should get very few queries because resolvers should learn about this. All right, so what does this mean in context of vendors? Well, what you want to do is have multiple vendors because a single vendor is, from one point of view, a single point of failure. So this is pretty straightforward, and this has been recommended practice for customers, large customers mostly, since at least 2016. So that's the background of why we're here. And so the question that we have to ask ourselves is, does this actually work, right? We've been recommending this for almost at least 10 years now, right? So does it work? So if you've seen me talk about stuff before where I've done any measurements, you know that one of my favorite sayings in the world is this Dutch saying, meten is weten. And basically it translates into English roughly as, to measure is to know, or maybe to measure is to know about. And so the idea is, if we want to know something, let's do an experiment, let's get some numbers and let's figure out what's going on. All right, so we want to do an experiment and we're going to set up two parts. We're going to set up the thing that we're querying and the thing that's doing the queries. So the thing that we're querying is a zone carried on authoritative DNS servers, and we're doing that, we're using two separate edges. Now in this experiment, we set up what's called a dedicated network at NS1. This is basically just an Anycast prefix that we have set aside for a single customer. In this case, we just use it for our experiment. The second edge that we used was Route 53, not because we did careful analysis and decided to use this for any specific reason. We just happened to have a Route 53 account lying around. So those are our two edges. Now, what does the zone look like? No DNSSEC, not because I hate DNSSEC, it just wasn't relevant for this experiment. I'll talk a little bit about that later. All the infrastructure records, by which I mean the SOA, the NS, the A, the quad A, all these, had long timeouts. I think it was an hour, maybe a little bit longer, I can't remember, but long enough that they should be cached throughout the run of this experiment. We didn't make any changes to the zone at all, so that was not a factor in the experiment. And the target of this is a single TXT wildcard record. It had a very short TTL, 5 or 10 seconds, something like that, enough that it wouldn't be cached for any meaningful amount of time. And we configured the text record differently for the Route 53 versus the NS1 edge, just so that when we looked at the data, we could try to understand what was going on. So that was the setup on the authoritative side. Now, on the side of what's doing the queries, we took advantage of the write batless network. If you've never used it, I recommend checking it out. It's a great system for doing ad hoc measurements like this and experiments. And basically the idea is that RIPE NCC hands out probes that people put in their homes, in their offices, in network infrastructure all over, and you can through the system basically request that it run a measurement. So I downloaded the full list of probes that were available at the time we ran the experiment, and then pulled out 200 candidates which looked good. We chose a mix of 80% American-based in the US and 20% scattered around the world, which in the RIPE Atlas network is going to skew towards Europe because that's where they're based. It's not super important where exactly they were, just we were doing this experiment on behalf of a customer of ours, and that matched what they needed. So those are the probes. What were they doing? Basically every minute they were doing a DNS query to this authoritative zone, to this wildcard that we had set up. And they were using whatever resolver was configured on the network that the probe sat in. There's a number of different ways you can do queries in the RIPE Atlas system, but in this mode, basically, whatever's in the DHCP server as the DNS resolver is what gets used. This way, it looks very similar to what it would look like for a person. And then as the experiment runs, it records all the answers that it gets back, including a bunch of metadata about it in the RIPE Atlas system, and you can pull it down through an API that they have. Right, so what was the actual experiment? Well, as you can imagine, we just withdrew the PGP from our edge, the one that we control. And the idea was to simulate the very simplest possible failure mode and see what happens. All right, so what do you think is going to happen in this case? Now, my expectation, and I've talked to a number of people in this room about what should happen, and the expectation is that immediately after the BGP route is withdrawn, you're going to see a number of failures because the resolvers don't know anything about it, and they're just going to start sending queries to addresses which aren't answering. And then very quickly, they should learn that they're not answering and send the traffic to the half of the edge that is working. So once that initial bump of failures completes, you should see a steady state where resolvers may be probing the non-working edge periodically, and you see a little bit of impact, but it shouldn't be too bad. That's my expectation, I think the expectation of most people. So what do we see, actually? And I'll show you some pretty graphs in a second. But anyway, the good news is that everything worked. There was almost no failures. However, there were a lot of really slow answers. And when you look at the data, it's pretty clear that these were because of packet drops, failures, and then retries. And so you see banding in the data, which usually is a strong signal that there's timeouts and retries, right? Because you don't expect networks to all of a sudden jump to 500 milliseconds, right? So that's what we see. And when we did the initial experiment, we kind of freaked out and we stopped it. And then we thought, well, maybe we just weren't letting it run long enough. It turns out it doesn't matter how long you let this experiment run. Resolvers are really stupid and they never ever learn that the world's a bad place. Yeah. All right, so a number of people reviewed my slides and said that they were really hard to understand, the graphs, which is fair. I just threw them into matplotlib in Python and made some graphs, which I guess maybe if you were like a PhD student in microbiology, it would make sense to you, but apparently to no one else. Here's a mini tutorial. I can use my little laser pointer. Yeah, so basically, on this axis here is the number of milliseconds. I scaled them so that all the graphs have the same one, so you can compare between the different routers. And then here is the outage, and you can see in this case there's a lot of slow responses, and then we restored normal service. We've got the number of RIPE Atlas probes, that's this before the @ symbol, and then the on the right there is the actual resolver target. So in this case, in this example, we had 29 RIPE Atlas probes that were using the Google public DNS, and I measured that by looking for the IP addresses that I could find about all of these public resolvers. So 8.8.8.8, 8.8.4.4, and the v6 and so on. Each color is, each dot is a single query, and the color represents a specific probe. So you can see, like this is the green one there, that was a single probe having these problems. Anyway, sorry for the complicated, I'm trying to get a lot of information in a small space. All right, so, oh no, that's really bad. Oh, there we go, good. The first slide here, this is the public DNS resolvers that I was able to check. Now this first one at the top is, The first one at the top here is Google. And like I said, there's 29 probes that were configured to use Google. Some probes were configured to use more than one server. I didn't detangle that in these. This is all just like absolute numbers. So you can see, as I mentioned before, these strong bands at like 500 millisecond, which to me indicates almost certainly that there's timeouts going on. And I stopped it at 500 5,000 milliseconds, 5 seconds. Because of the number of servers that we had, there ended up being 6 addresses, I think. So nothing took longer than that. They would have tried all of the available ones. Anyway, then Cloudflare, you see, had a little bit of impact during the outage, but not nearly as severe. I don't know why this is. Yeah, thank you. Cloudflare, I've heard that they have shared cache between their things. Maybe they share state. Maybe they just have a lot lower TTLs. They may like give a 10 or 20 millisecond and then retry. They may be more aggressive, I don't know. OpenDNS, similar situation, a little bit of problem, but not much. Quad 9, similar banding to Google. And I talked to one of the Quad 9 engineers, and I'm pretty sure I understand that, but we'll talk about that in a minute. This slide is super dense. I don't expect you to read it. These are other resolvers in the public space. A lot of people were configured for RFC 1918 or private IPv6 addresses and things like that. I didn't include those because the reason for that is that you have multiple different DNS implementations at those, and it's really hard to extract signal out. What's important for this slide is that you see different kinds of behaviors. So in these two, these are both in the same /24, you see it looks like they're doing retries and getting only a single type of banding here. This one looks more like the Google or Quad 9, different heights of the bands. This server didn't have any problems. My theory about that is that they're using a resolver that just goes to the fastest answer, and whatever that was happened to be a Route 53 one, so they didn't experience any pain. This, much more like Cloudflare, where they had a little bit of problems. This one here is what I actually expected to see everywhere, which is that it was mostly fine, but you see periodic probing of the other IP addresses with the associated timeouts. Now, again, the important thing for this is not any particular behavior, it's that there's a whole bunch of different kinds of behavior. All right, so why do we see these results? Public resolvers, some of them do not share cache. And what that means is that they don't have consistent routing based on your source IP address. That means that when my resolver goes to a 8.8.8.8, it's going to end up at a different recursive resolver, which doesn't share any state about the status of these IP addresses. So basically, every time it's got to try to figure out which ones are bad and which are not. Yeah. So, and if you share cache, you may not be sharing cache information about IP addresses. You may just be storing actual ones. And so our test may be carefully designed to defeat the common caching behavior of these public resolvers. Other possibilities, like for the ones which aren't public resolvers, maybe the software just doesn't track RTT. Maybe there's some like dissonance between the algorithm that's used and this experiment. There's a whole bunch of different possibilities which are basically we can't know what they are. And I argue it's not actually important for us to know these. All right, so what does all this mean? Don't panic. Everything did work. The answers all came back. It was just a delay. So depending on your use case, this may be just totally fine. You pick a reasonable TTL. Most of it will get cached. Every now and then, a customer will get a slower answer, but it's basically fine. I haven't actually tested this, but I'm quietly confident that that's what's going to happen. Now, if you have a zone that's highly dynamic, you probably are doing traffic steering or other types of responsive things, and then it's really important for you. And these are the zones that really don't want delays and timeouts. And so these things are in a bad state. So what do you do about it if you're in this state? Well, unfortunately, we don't just, my hope was that maybe one public resolver would be the source of problem, right? But we see at least two of them are, and we can't just ask Quad 9 or Google to fix their stuff because it seems like it's widespread, the behavior that we're seeing now. And it's not like we can just fix one code base, because looking at the graphs, I think there's a lot of different resolvers which experience problem in this case. So my own thinking is actually we can't fix it, at least not easily, and we can't fix it quickly. What can we do about it? Can we work around it in the DNS itself? I think probably not. I tried to come up with some clever ways to fix it, but it was a bit like trying to overcome entropy. You know, you try to think of ways to move things around and make a perpetual motion machine, but it's not going to work because ultimately the resolver has to make a decision about where to go, and if that's not happening properly, you're going to end up in the same state. Can we work around it at the networking layer? Maybe. You can do things like covering prefixes which fall back and things like that, but that requires cooperation among organizations doing the routing, at which point you're losing your your goal, which is to remove single points of failure. And it's a complicated system, hard to debug, and you're gonna have a hard time convincing large DNS vendors to cooperate at that level. So I'm not sure, I don't think that's an actual solution. One solution which probably would work is to just pick different names for your application. Then they can each have a fully independent DNS resolution path. That's gonna require that you actually have control over applications, and like web pages aren't gonna work this way. And you actually have to then think about the logic and build that into your application. I think that's a reasonable solution for a lot of cases, but it's not a generic solution that we can just apply everywhere. What can we look at more? Well, like I said, this is literally the very simplest failure scenario. Anywhere up the tree can fail, at the TLD level or at the root level. You can have failures with the network itself. You can have partial failures, which I think are a lot more likely, like one pop being down or things like that. You can also have a whole bunch of things which are kind of failures which are hard to identify, like a DNSSEC bug, empty non-terminals doing things wrong and stuff like that, only on one vendor, right? Or things like a zone truncation, which hits like only a few of the servers. These things are hard to find. So that's looking at all those things, I think will yield interesting results if people want to do it. You can also go into the software that's causing these problems. Maybe we can squash all these bugs. Maybe there's only like four or five implementations and we can find them all and get them all to behave better. I don't know. We can also look at optimizing how we arrange our zones in terms of the name servers and the IP addresses. One interesting thing is that an artifact of my test is that everything did work. If you added a few more IP addresses, then very unlucky customers would by chance only hit bad IP addresses and get an actual failure before their 5-second or whatever timeout in their application hit. So that's something to look at. Anyway, that's basically it. Conclusions, DNS remains surprising. A naive approach to setting up your multi-vendor authoritative edge may not be ideal depending on your use case. You can probably improve the redundancy, but I'm not exactly sure how. And if we look into this deeper, then it's gonna be probably even uglier. That's it.
Hey Shane, is this on? Yep. So thanks for this presentation. I think this is very useful research, and I think we need to do more of it to understand resolver behavior better. And so I certainly agree that to measure is to know, right? So, but the other way there are other ways to know things, such as whether you've deployed these kind of configurations and your customers are yelling at you during an outage or not. That's a pretty good indicator as well. Yes. The other way to know is to do, not these kind of synthetic benchmarks, but to do there's different classes of measurements you can do. You can do RUM, real user measurements, where you have probes sitting co-located with the customer, which actually show you what the customer sees during these events, right? So that's another way. True. It's more involved, of course, to set up those experiments, but that's certainly, I think that's another avenue worth exploring. I just wanted to say a little bit more about our experience. As you know, we're one of the companies that does this, at least in some parts of our infrastructure. And our experience is, by and large, it works. So we've had cases where we've survived outages of a single vendor because the other vendor was up. We've also had the converse situation where we've had a zone temporarily deployed on one vendor, and that vendor experienced catastrophic DDoS or some other severe degradation. And the way we fixed it was by rapidly bringing in the second vendor, and then within minutes to hours, modulo TTLs and such, customer complaints went away, right? And the other point before I forget, the other point I want to make is this problem space is not only limited to multiple vendors, because you can have a single vendor that has multiple implementations, where one implementation had a bug, and resolvers, of course, don't know that your name servers are spread across X number of vendors. They just know there's a bunch of servers to talk to. And this applies just as well. So we need robust and rapid resolver failover behavior, regardless of how many vendors people have.
That makes sense.
Okay.
About your suggestion about updating the vendor that's being used or the configuration, that's certainly a possibility. It's tricky to automate because it relies on monitoring, and then you've always got the question of, is it a false positive and things like that. I mean, you can do it by paging your NOC, but then they've got to do a similar sort of thing. So I consider that it may be the best that we can do in a lot of cases.
Yep. Okay, yeah, but thank you. Great presentation.
Yeah.
Hi, Shane. Dave Knight, Verkara. Great presentation. So I did some similar work, presented that at RIPE about 1.5 years ago. So I had a couple of comments on your technique. So you used short TTLs. Did you think about using cache-busting queries to just absolutely guarantee that you weren't getting cached answers? Or was that hard to do with Atlas?
It's, as far as I can tell, it's impossible to do with Atlas
Okay.
without chicanery. So.
Right. And then you said that you withdrew BGP prefixes. Did you think about, rather than doing that, just breaking the name server so that you still see the queries, so you can still capture the queries coming in and know where they're landing rather than just not seeing them at all?
We did not, because in our experiment, we didn't think it would fail.
Okay, and
that's an interesting idea. That could be
Right.
quite useful, actually. Yeah.
and then another was like, you had observations about the behaviors of different resolvers, particularly the cloud ones. So I had a question related to that. Was, did you withdraw the prefix? Did you use V4 and V6 first of all? Was the question?
At least we used V4.
Okay, because
I'm pretty sure it was configured for both prefixes.
Okay, because what I was going to ask was, like, if you're withdrawing the prefixes in both address families for one name server, Cloudflare hates IPv6, OpenDNS loves IPv6. So if you withdraw both, then you're going to see skewed results from them because they really love one. If you weren't withdrawing both at the same time, you might see something skewed because, they don't know. Cloudflare won't notice if V6 goes away. They never ask V6. Likewise, OpenDNS never ask V4 if V6 is supposed to be working. And then the other observation is that, as far as I can tell, Quad 9 uses multiple resolver implementations behind the same address. So understanding its behavior is always going to be very mysterious.
Yeah, I talked to a Quad 9 engineer last weekend at FOSDEM and got a little better understanding. They use a load balancer, I think DNS-dist, I forgot to ask, which does do some caching. But again, that'll cache the records at the very best, which this won't help because this is about the infrastructure, not about the data. So,
right.
Yeah. It's interesting about the V4 and V6. I will look at that because that would be relatively easy to test.
Mm-hmm. Yeah. Thanks.
It actually didn't matter that you were using Route 53 and NS1. You were testing resolvers. It would be interesting to understand if you instrumented your own authoritative name servers across a distributed platform, brought down one or two or whatever, because it's the same test, but now you've got control of the answer side. You're actually seeing who's asking you and how many times you get queried. Because the real question is, when you blow out to a few seconds, how many queries were received? And even when everything is normal, how many queries are actually posted to authoritative name servers? The work we've done in APNIC tends to suggest that even when things are fine, most of the time you generate between 2 and 3 queries for each successfully answered name. The DNS is extravagant. And when you start to take one down, not only do you get delay, but you also get query storms. And it's kind of interesting to look at this from the other side, and it seems your experiment could quite easily accommodate using more than NS1 and Route 53, go roll your own. Thanks.
Yeah. Interesting suggestion, yeah.
And I will relay one more question from Ben Schwartz. And the question was, could this be turned into automated test in a web page, which maybe is question more for Jeff Houston, who just spoke, instead of you?
Could it be turned into automated testing what?
Yeah, embedded in a web page so you can have more data from more clients, not just RIPE Atlas.
I don't think. Oh, Jeff says yes. Yes. All right. Thank you.
Thank you.